So in this part of the experiment, which actually has a pre-lab written up, which you should have written in lab the first week, and there was also a video available if you missed the first week, basically what we're going to do is we're going to make a 3% saltwater solution. We're then going to aliquot 3 5 milliliter portions of the solution. We're going to remove the water, and we're going to measure the mass of the salt that's remaining. Then we're going to determine the accuracy and the precision of this experiment. In this case, the first step is to make the 3% saltwater solution using the salt and the water that you can see on your screen. After that, we're going to move 5 milliliters of the solution into 3 massed 50 milliliter Erlenmeyer flasks. After that, we're going to boil off the water using a hot plate, and then finally measure the mass of the residual salt. We'll then use these numbers and Excel to determine the precision by calculating the standard deviation and the relative standard deviation, and the accuracy by determining the percent error. Jesse will now show you how the solution will be made. All right, so before we get to Jesse showing us how to make the solution, I want to go over weighing by difference again. All right, you should have done this last week during the first week of lab, but I just wanted to show it to you one more time. So in this case, we want to add 0.74 to 0.75 or 76 grams of salt to this, and then 24.2 milliliters of water to make a 3% solution. Often in real life, we would actually calculate the solution concentration, but we're not going to do that today. So I'm going to do this by difference. And the reason we weigh by difference is because we don't want to transfer chemicals over the balance. Because if we spill chemicals on the balance, then that causes problems, okay? So we don't want to contaminate this. We don't want to ruin it. It's expensive. So what we're going to do is we're going to get our salt. This is just sodium chloride, table salt, all right? And we're going to get ourselves a weighing bottle like this. You'll notice I'm wearing gloves and a lab coat because it's good practice. I'm also wearing goggles, but this is just salt. So it's relatively harmless, right? I wouldn't eat it or anything, but it's relatively non-toxic. So what I'm going to do is I'm going to open up my salt container, and then not over the balance. I'm going to use a scoopula to transfer in some salt, and I don't want that big chunk, so I'm going to pull that back out, and just the powdered salt like this, okay? If you have big chunks like this, sometimes you can break them up with the scoopula. Sometimes there's other ways to do that, but for now, that's basically what we're going to do. Now, I have some salt in my weighing bottle. So if we look here, all right, for the amount of salt, I've put in about, that much, all right? Maybe 20% full. In the weighing bottle, I've put in the salt. Now, I want to record the mass of the salt and the weighing bottle, all right, once I've added it in. Notice I haven't weighed anything yet. So in order to do that, I'm going to zero the balance by pushing this button, the 0 button. That makes the balance read 0.00. I'm then going to open the balance, place the chemical on the center of the balance in the weighing bottle, and then I'm going to close the balance. I'm now going to record this in my Excel file with all of the digits. So I'm going to go ahead and pause the video and do that, and then I'll be right back. So if you had a keen eye, you may have seen this last digit changed between 17.7006 and about 17.008. I put it down as 17.007 because that's what I was seeing when I recorded the mass. But note that this decimal might change a little bit, but this is 1/10 of a milligram. So for 1/10 of a milligram off, we're pretty okay. So that's okay. Just go ahead and do that. Note that if I open this balance, it will jump around a little bit more depending on the airflow. So you want to keep the balance closed, okay? Now I'm going to take this off. Now, you'll remember that that was 17.007 grams. I need to add 0.75 grams in here. So I'm going to subtract that. You can use a calculator. I'm going to do it in my head. And basically, I'm going to find that I want about 16.95 grams in here remaining once I spill this out. So what I want to do is I want to be super conservative. Okay, so I want to be very conservative and just add a little bit of salt. Notice that I'm not using the scoopula to do this, because if I use the scoopula, I'm increasing the probability that I'm going to spill it on the bench. And if I do spill it on the bench, I'm going to clean it with a wet paper towel. And if it's some chemical I'm not sure what to do with, I'm going to ask the TA. But I'm not using this to scoop it out into here, because then I'm increasing the chances I'm going to spill some on the bench, and then I'm not going to have the right mass that's in here. So I was very conservative. I don't think that's 0.75 grams. I'm going to put this back on the balance, okay, and I'm going to read it again. Remember that before it was 17.7 grams, roughly. All right, so I'm trying to get down to about 16.95 grams in order to have 0.75s transferred. Note that I've only transferred here about 0.25 grams. Said another way, I've transferred about a third of what I want to transfer. Well, now I know what a third of what I want to transfer looks like. So I can use that to try to estimate and add another 2/3. Notice, and I didn't say this before and I should have, this flask is dry. That helps us. This weighing bottle needs to be dry when you use it. So if at all possible, use a dry flask. That way you can take some out if you need to. If it's wet, that's not really possible to do. So I'm going to, using that amount, I'm going to spill out a little bit more, okay, that I'm going to guesstimate is about the right amount. All right, now I have about that much, which I'm hoping is about 3 times more than I had before. So I'm going to take this, put it on the balance again, and I'm going to record the mass. All right, so what you'll notice is now I have 17.1. I again want to get down to about 16.95, so I need to add a little bit more. It's always better to be conservative because it's always easier to add more than to take some out. All right, so now I'm going to repeat one more time. I'm going to just put a tiny bit of salt into here, like so. I'm going to weigh it again. Okay, and you notice this is going to be, several times through. That's not quite enough out, so I'm just going to do just a little bit more. It's hard when it's this small of an amount. And then I'm going to try again. And then what you're going to find is that after 3-4 times, hopefully I can get it into the right amount, and I need just a touch more, and I'm being extra careful because I know the video camera is watching me. So I'm just going to add just a touch more, like so, and hopefully that'll do it. I want to put that kind of in the middle as best I can. All right, and now I'm still a little bit short. All right, sorry for making you watch all this. So I'm going to, ooh, I added way too much. After all that, I added way too much, and now I probably overshot it. Nope, I got it perfect. All right, 16.9577. So luckily I added what I thought was way too much, and it ended up being about the right amount. So now what am I going to do? I'm going to record this again. If you have a completely dry flask, you could theoretically transfer it back the other way if you added too much. If you add a tiny bit too much, you don't want to way overshoot this. You want to go slow so that you can get the right amount. Keep in mind, for this lab, I'm only doing this once. So if this process takes me 5 minutes, it's not a huge deal. So to review, what did we do? Well, let me just show you the math, and then we'll review. So what I'm going to do is I'm going to swap over to Excel, and I'm going to put this number into my Excel file. All right, so now I've got both the numbers in my Excel file that I just wrote down from the balance, those numbers that you saw. Okay, now I want to find the mass of salt. In order to do that, I'm going to simply hit equals. That tells Excel to do math. Click the initial mass, subtract out the mass after I added some, took some salt out, and I find that there's 0.7424 grams of salt missing from the weighing bottle. Well, I put that salt into my 125 milliliter Erlenmeyer flask, so I can be confident that there is 0.7424 grams in my Erlenmeyer flask. Notice that the most important thing here is I transferred no chemicals over the balance. It's going to be very obvious when students transfer chemicals over the balance. Why? Because there's going to be chemicals on the balance. Now, could you wipe those up and we may never notice? Probably, but if you knock them down into the inner workings of the balance, then they cause other problems besides just rusting problems. So it's not good to transfer these types of chemicals over the balance. They are corrosive. They're not good for the balances. That's why we weigh by difference. It's very important to do that. So as promised, I said I was going to review. So let me put back up the balance and we'll review. So first thing I did was I had my empty weighing bottle. I did not measure the mass of my empty weighing bottle. I added about 20% full of the weighing bottle with sodium chloride. Notice that I added way more than I needed, okay, which is totally fine. Now, if we're working with advanced chemicals where we're being super analytical, we might tell you not to put this back. But for today, you can just put this back in the salt. It's just table salt, so it's not going to be super contaminated, and it's not super pure to begin with. Okay. The second thing I did was after I transferred in this amount, I made sure that I closed and zeroed my balance. Once I closed and zeroed my balance, I measured the mass of the salt and the weighing bottle. Once I had that mass, what I wanted to do was I wanted to pour or spill the salt directly into the empty flask. The flask isn't empty anymore, but we spilled the salt into the empty flask. We recorded the mass again. Notice that if we were doing it this time and it was a new flask, we'd want to go down to about 16.2 grams, all right? Because that's 0.75 less than what we have right now. And that's constantly how we're doing it. All right, we're going to be conservative. We're going to spill several times. We're going to make sure that we don't super overshoot it because we don't want to be taking salt back out of the flask. Now that we have the salt in the flask, Jesse will show you how to make the solution. I do want to point out one last thing, which is that it really is imperative that you guys are using the weighing by difference technique because it's good practice. This is the type of thing that they're doing in different industries to keep their balances clean. You have to have clean balances in order to get accurate weights, and we need to have accurate masses, so we need to keep our balances clean. So please use the weighing by difference technique. In this lab, we will not go on to figure out the exact concentration of the solution. We will just assume that it's 3% because it's very early in the course. But if we were doing more professional type chemistry, we would figure out the exact concentration of this solution by adding the water, recording the mass of the solution, and finding the exact mass percent. But we're not going to do that here. So I'm going to turn it over to Jesse, who's going to show you some more parts of the experiment. Thanks for watching this part.
Colin was saying we have our salt and we have our water. I've measured out 0.75 grams. You want to be between 0.74 and 0.76. And we have about 24.2 milliliters of water here. So to make our salt water, bring the water to the salt and we swirl. Erlenmeyer flasks are very good for making solutions in because their shape lets you swirl them without splashing everything all over. You would never want to try this in a beaker. So once that is good and clear, with no salt floating around, you are ready to move it into your massed 50 milliliter Erlenmeyer flasks. So I've massed my flasks, which are labeled. Make sure you label them before you mass them. Ink does have a mass of its own. So now I'm going to put 5 milliliters of saltwater solution in each. We're doing 5 milliliters in this video because that's what we're doing for this year. Your year may be different. Make sure you check your manual. So we take our salt water and we take our graduated cylinder. Now because the mouth on this is a little bit narrow and the mouth on the flask is a little bit big, I don't really want to pour this over and over. I'm not measuring that much, so it's not going to take that much time to just pipette it to 5 milliliters. So once it's close, put it down on the bench and get down to eye level with it. That was to knock out an air bubble, so I need just a drop more. You want to make sure you're getting 5.0 milliliters because that will change your mass. So once we have that, we pour that into flask number 1. Give it a quick jiggle, knock everything down, and repeat. Once you've transferred your solution, you can place it on a preheated 350 degree hot plate. This hot plate is extremely hot. It has been warming up for about 5-10 minutes. You should do that before you start making your solution so it has time to come to temperature. Gently place them on. Don't worry about the cool liquid inside. It won't cause a problem. This isn't that hot. And now let them sit for 20 minutes until they are completely dry. So this is set to 350 degrees Celsius. This is extremely hot. That's 600 degrees Fahrenheit. So please make sure all cords, your hands, and anything else that will not do well with 600 degrees applied to it are kept well clear of the hot plate. You can observe it from a distance completely safely. Your goggles need to stay on at all times. So, these have gone for about 7 or 8 minutes. However, notice that they are full of water droplets. This is not what you want. You are not done yet. You need to let this go for the full 20 minutes. Those water droplets all have a considerable amount of mass that will throw off your calculations if you weigh them now. Let this dry for a while longer. So now we've gone for a full 20 minutes, and this is what you want to see. These are completely dry. There is no trace of water in them. We do have some salt up on the sides. That's okay. Now these flasks are extremely hot. So first, I'm going to turn the hot plate off for safety purposes. Alright, so you see, that is now off. These flasks are going to be extremely hot for a little while. They're hot enough to boil water. That means they're hot enough to burn you. Let it cool until you can touch the top and put it on the bench. Then let it cool for another 10 minutes or so, or until it can be comfortably handled. Once they're cool, you will mass them on the balance. Because you have them labeled, you will be able to put the correct masses with each one and find the amount of salt in each flask. Now I'm going to turn you over to Colin, who's going to walk you through the math.
So now Jesse has cooled the flasks, and we've recorded the mass of our 3 trials. There's a few things to note here. First of all, it's not worth burning yourself in the chemistry lab. So if you have to wait an extra 5 minutes to make sure the flasks are cool, please do so, because you don't want to get burned. The next thing is that you'll notice we needed to know which flask was which. So Jesse clearly labeled all the flasks 1, 2, and 3. So flasks 1, 2, and 3 were labeled, and then we recorded them once the salt was added. We recorded all of our mass measurements to 4 decimal places. It's really important that you write down all 4 decimal places for all of your masses. We now need to find the mass of the salt in each flask. So if we take the mass of the flask with the residual salt and we subtract out the mass of the original flask, we can find the mass of the salt. Note, to tell Excel to do math, we hit the equal sign. We can either type in C2, which is what we want to use to subtract, or we can simply click on cell C2. We then type in minus on the keyboard, and then we put B2, which we can either type or click. We then hit enter. This gives us the mass of the salt in the flask. We can then drop this down. So I'm grabbing this right here. You'll notice that the plus sign changes. So the plus sign here is like a big plus sign that's white in the middle. And then it turns to the smaller plus sign that's black in the middle when I hover over this little box right here. I then drag down, and it will now subtract each subsequent cell. And you'll notice that we have 0.1484, 0.1475, so on and so forth, grams in each of the flasks. It's really important to note that these have the correct number of significant figures. Oftentimes, Excel will give you incorrect numbers of sig figs. There is ways to fix that, but they're pretty complex, so we're just going to be okay that if the calculations don't have the perfect number of sig figs, that'll be okay. Note that when we draw our conclusion and we write out our conclusion, we're going to make sure that it has the proper number of significant figures. So the next thing we want to do is we want to calculate the average of this data. So to do that, we type in equals, and Excel knows how to find an average. So we type in the word average, and then we open a parentheses. Once we do that, we could simply click on our data. So I'm clicking on the top one, I'm holding the mouse down, and I'm pulling through all of the data, dragging through all the data that I want to take the average of. You can then either close the parentheses or simply click enter, and Excel will close the parenthesis for you. Note that the average doesn't have anywhere near the correct number of sig figs, but we're not going to worry about that so much in Excel because, again, it is a little bit of a pain in the neck to correct that. We next want to calculate the standard deviation. Excel knows how to calculate the standard deviation, so we're going to type in STDEV. We're going to open a parenthesis, and we're going to select the data we want to calculate the standard deviation of. Again, I highlighted all of the data. I do not want to include the average in my standard deviation calculations, and I click enter. So now we now have the average and the standard deviation. The relative standard deviation is the standard deviation divided by the average times 1,000. And this gives us it in PPT, which is parts per thousand. So equals the standard deviation, I just click it, divide by is the slash, then I'm going to click on the average, and then I'm going to multiply, which is the star key above the 8, and I'm going to type in 1,000 using the keyboard. This gives me the relative standard deviation, which in this case is 15 parts per thousand. So Excel is able to do all of this math, which is why it's really important that you learn how to use Excel. Excel is also useful for many other things besides calculating chemistry stuff, so it's a good idea to learn how to use it. Note that in this case, the relative standard deviation is a comment on the precision of the experiment. In this case, we get 15 parts per thousand. This is a relatively low relative standard deviation. Note that a perfect relative standard deviation would be 0. In order to get a relative standard deviation of 0, all of these data points would have to be exactly the same. You'll note there is a little bit of deviation in our data. So there is not perfect precision here, but there's relatively good precision in our experiment because we have a relatively low relative standard deviation. Note that if your relative standard deviation comes out to be 250, that's a relatively high relative standard deviation for this experiment, and most likely occurred because not all of the water was evaporated. So draw your conclusions based on the data that you have. In order to find the percent error, I first need to find the accepted value. So what do we know? Well, we know that we have a 3% mass per volume NaCl solution. And what else do we know? We know that we took 5.0 or 5.00 milliliters of this solution in each of our 3 samples. So you'll remember that Jesse put 5 milliliters into each flask. And we also know that it's a 3% solution. Well, if we have a 3% solution, we can write this as an equality. What is the equality here? What the equality is that 3.00 grams of NaCl are in 100 milliliters of solution. You'll note that a percentage is the part out of 100. So we have 3 parts, 3 grams, in 100 wholes, in this case 100 milliliters. We now need to use this equality as a conversion factor. So we want to multiply like this. Well, we want to get rid of milliliters and end up with grams. So we put our 100 milliliters on the bottom, and we put our 3.00 grams of NaCl on the top. And when we do that math, so we take 5 times 3, which is 15, and we divide it by 100, we get 0.15 grams of NaCl. Now, if we were going to technically have the correct number of significant figures here, we have 3 here, we have 3 here. This 100 is exact because it comes from the 3%. So technically speaking, we have 0.150 grams of NaCl with the correct number of sig figs. So this is the accepted value. This is how much sodium chloride or salt we expect to find in each flask. Once we have the known or accepted value, we can then calculate the percent error. So now that we know the accepted value, we can find the percent error. The percent error can be calculated in several ways, but in this case, we're going to calculate it based on the average. So again, to tell Excel we're going to do math, we're going to hit the equal sign. We're then going to use the absolute value function. The absolute value will return the difference between 2 numbers independent of the order. We're going to take the accepted value, which is 0.15 grams. We're going to subtract out the average value. All right, in this case, we wouldn't actually need to use the absolute value because this is going to be a positive number, but it's not a bad idea to put it there. We're then going to divide the difference between the accepted value and the measured value by the accepted value, in this case 0.15 grams. Because it's a percentage, we then want to multiply by 100. And this tells us that our percent error is 0.4889%. Note that Excel doesn't do very well with the sig figs again, so we're just going to go ahead and ignore that, but we are going to try to report them correctly in our conclusion. So what conclusions can we draw from this data? Well, we can draw two major conclusions. The first thing is that our data was relatively precise because our relative standard deviation was 16 out of 1,000. Precision means reproducible. If you look at your data points, you see that these data are relatively reproducible. Said another way, these numbers are relatively close to each other. What about the error? Well, the percent error here is very low, and you might not get quite this low of a percent error, but the percent error is very low because if we look at our average value, it's 0.1492 or 1.1493, and the accepted value is 0.15. So our average is very close to our accepted value. Don't worry if your average isn't quite this close to the accepted value. Do note that your percent error and your relative standard deviation will be way off if you don't let your flasks dry completely. Please make sure you allow at least 20 minutes for the flask to dry completely. That should be plenty of time. We appreciate you watching this video. We hope that you enjoy this course, and we look forward to seeing you in future videos.